recording. So everyone needs to okay. So yeah, thanks. All right, so let's start today. So hi everyone. So it's me again. So today we'll talk about two-body interactions. At the start, that might be like very unfamiliar. So what does two-body interactions mean, right? So let's just start with a very simple example, just like how we did last time um about the bead on rotating hoop. But this is not a bead on rotating hoop. It's a similar system that we sort of encountered last week. So let's consider, there's a block of mass m1, all right, and a block of mass m2, okay, and they are coupled together, okay, they are connected. Oh, oops, okay, they're coupled together with a spring, okay, with spring constant k, all right. So let's just do the same thing as we done last week and see, okay, what comes about in this system, okay, and how does it matter with how does it connect with two body interactions, okay. Well, obviously there are two bodies here, there's mass 1 and mass 2, and then they're going to interact with this spring over here. So let's just again, the first thing we do is to write down equation motion. So let's just take the position of the mass 1 from this wall over here. So let's take this as the origin, right? And then the position of mass 1, let's call it x1, and the position of mass 2, let's call it x2. All right. And let's just write down the equation motion and see what this tells us. Okay. So the first thing that you can write down for mass m1, the mass 1, is that its acceleration is equal to the only force that it has is the restoring force of the spring, and this is basically k x2 minus x1, which is the elongation. So let's assume that the natural length or the relaxed length of the spring is equal to 0. Okay, so basically how much it elongates is basically the difference between the difference in the positions of the two blocks. And this block, when x2 minus x1 is non-zero, basically this basically pushes the block to the right, so it's a positive x2 minus x1. All right, and then for mass 2, the same thing happens. Okay, this time you don't even need to know don't need to even analyze direction, because you know that the spring here connecting the two is an internal force of the system. So this must be negative t minus x2 minus x1, and this is just from Newton's third law. Okay, so this is from Newton's third law. How do I? Okay, Newton's third law. Okay, and so from last week, you surely know, okay, how to solve this system. Okay, you've learned a little too about it. So does anyone have an idea like what's the way to analyze the system? Like what's the most reasonable thing you can do in terms of the equation? What can you do to understand the dynamics of the system? No? Does anyone have an answer? Okay, if not, I'll just give off. Let's just start with something. So the first thing you can do is saying that, okay, on the right hand side, one of the forces is one of them is negative in the negative direction of the other. Okay, just because the spring is both trying to pull them together. So one thing you can do is just add, the first equation to the second equation, and you get m1 x1 double dot plus m2 x2 double dot equals 0. Okay, so this is the first thing that you get. I don't know if Zizun has taught you about this somewhere else, but if you remember, like, so what is this? Okay, so this is basically something that we call, if we divide this entire thing, let's use a different color, by the total mass. If this is the total mass, m1 plus m2, basically this is telling you that the center of mass, let's use x, the acceleration of center mass is 0, where the acceleration of the center mass, where the center of mass position is defined by m1 x1 plus m2 x2 divided by m1 plus m2. All right, so this should be, hopefully this looks somewhat familiar to you. This is basically saying that, okay, so if I have m1 equals to m2, xcm is equal to, if this is equal to m, then it's basically x1 plus x2 divided by 2, which is, for the two block system, this is what you assume, what you would expect. Sorry, that the center of mass is in the middle of the two, and if you have some mass one that is larger, okay, then the position of the center of mass goes further to the left and such on. So just analyzing the dynamics, we can know that, okay, there's something. There's one. If you add the two equations just together, you find that, okay, in this system, when the two bodies just interact via a mutual force, the first thing that happens is that, okay, the center of mass basically does not accelerate. Okay, so there's no force acting on the system. There's no external force acting on the system. All right, and basically this tells you that the center mass position is equals to the center of mass position at the beginning of time plus the velocity of the center of mass at the beginning of time times how much time has gone. Okay, so that's one thing that you have seen before. Another thing we can do to get a nice equation of motion from 1 and 2. Okay, so I'll just write it again here. So m1 x1 dot equals to plus kx2 minus x1, m2 x2 double dot equals to negative k x2 minus x1. So one trick we can do is to divide m1 from the first equation. Okay, this gives you x1 double dot equals to k over m1 x2 minus x1, and divide the second equation by m2, which gives you x2 acceleration equals to negative k over m2 x2 minus s1. All right. So for those of you who just joined the meeting, basically we're analyzing the system with of two blocks with a spring connected with a spring constant k. With different masses. Okay, so these are the equation motions, and this is I just divided them by the mass. And one thing you can realize is that you could just take the two equations and then take the difference of the two equations, and what you get is something neat. So okay, let's just do this. Right, so basically what you get is x1 double dot minus x2 double dot equals to k. Okay, because k and x2 minus x1 is the same, I can take out the common factor, and then it's divided by 1 over m1 plus 1 over m2. Okay, because this is what's left of the two. And then what you can see is that if I define x, okay, as x2 minus x1, you can get that the time derivative of x, okay, the acceleration of x is equals to negative k, because x2 minus x1 is here. This is minus kx multiplied by something like this. If I take the if I bring the fraction to this form, I can also bring this fraction to the left hand side, and I get a nice equation, which is something quite cool. It's mu double x double dot equals negative kx, where mu is just this factor that I put to the left hand side. Okay. This is sort of interesting. So what this tells us? So there's going to be a dynamic of like the dynamics of the system can be reduced into two things. One is that the center of mass basically does not accelerate, so basically just move on at constant velocity. And there's another degree of freedom, which is basically the relative position of. So let's think about this. This x, what is this? Is x2 minus x1 is the relative position between the two blocks. Okay. So this is x. Okay, is the relative position between the two blocks, and the relative position between the two blocks is basically just given by the same formula for the spring with the internal force between the two blocks, right? So this gives us something interesting, that this two-body system, like this block of M1 connected to a block of M2 with an internal force, can be reduced to the relative position. So instead of understanding the degree of freedom of x1 and x2, the two positions of the box from an origin, I can reduce the system into a center of mass which doesn't move, and then something called reduced mass, which is this mu. Let's call it the reduced mass. Okay, this reduced mass here, and for in this system, the center of mass does not move and it's just fixed on the table, and then these two are connected by a spring of the same spring constant k. And then basically you're just trying to understand the distance, the position of the reduced mass from the center of mass. Basically it's just basically this system is just quantified at mu x double dot equals negative kx. All right, so and you can basically, what you have done here is basically saying that, okay, in the rest frame of the center of mass, a two-body system of mass 1 and mass 2 can be completely written as a system where the center of mass is fixed, and then there's a reduced mass. There's some mass over here that's not really M1 nor M2, but a combination of both using this formula. And this is just undergoing the same force as the initial system, all right? And it does whatever it does. Sorry, this should be x. And the motion can be completely described by this relative position between the reduced mass and the center of mass. Okay. So this is not just true for the spring and block system, but because the only thing that we've done is because we have two masses, M1, M2, and then the only thing we have assumed that they have a force, a mutual force. Okay, that's the same. So let's say that sorry, let's not put the minus signs here for now. Basically, they're attracted by the same force in just a different direction, okay, based on Newton's third law. And for every time we do this, we can always decide for an origin, okay. and even assign the two masses a vector position. Okay, and then this is all this these equation motions for these people can always be written as m1 r1 double dot equals to the force between the two fr. Okay, in the direction of, so in this, so let's say that, so this is r equals, this is x equals to r2 minus r1. Okay, so this is in the x direction. This is in the negative x direction. And then the second body will experience an acceleration given by the force from mass 1, but it's pointing in the opposite direction of this. You can always do this trick, all right? The first thing you can do is always add the two equation motions together, and what you always get is that the center of mass move with constant velocity. It does not experience any acceleration. Maybe I should write that this is mRCM. This is the first thing you can do. And similarly, for the second thing, you can divide by m1 for the first one and divide by m2 for the second one, and you always get r2 minus r1, which is x equals to equals to f of r in the x direction. Sorry, with the reduced mass. I think this is in the negative direction, if I'm correct. Sorry, r2 minus r1. Yeah, okay, yeah, that's correct. All right. So this is why like understanding two-body interactions is something that's much more general, and why we're making it as a topic is that every two bodies that experience the same mutual force, okay, by Newton's third law, can always be decomposed into this the system where the center of mass basically is not accelerating, and all the dynamics captured between is captured in the relative position of the two objects, and then they obey the same force laws that the individual system has, just in terms of the relative coordinates of the relative positions between the two. Right. Are there any questions up to now? Has everything been clear? Okay, no? All right. Okay, so hopefully this gives you a very general view of what we're going to do today. Basically, we have identified that all two-body systems can be, all two-body interactions can be boiled down to something that's not very exciting. Basically, the center of mass basically just goes with constant velocity. But we're gonna analyze this system. Okay, this system is interesting because it's something that's one-dimensional. I mean, like just in terms of only one degree of freedom, like the relative positions, and hopefully, that's exciting about it, right? So the first thing that we can try to understand is like, okay, are there any interesting conserved quantities, right? So remember that we're always excited about things that are conserved, like energy, like angular momentum, and so forth. one thing that we can see is that, okay, when we reduce the two body system into something that's fixed, so reduce M1 M2 something that's fixed, and like this reduced to this with a reduced mass getting the same force, okay, we can see that this force is something called what we call mutual forces, are central. What that means is that it always points towards the center of mass. It always points towards center of mass. And if you heard about this, you know that these, like, if we look at something called the torque, if you remember the torque, which is sorry, this is f of x. This should be just f of x. So they only depend on the relative position of the two bodies. So if you remember, something that look about is the torque. You find something very interesting, right? So the torque is always 0 because the force always points in the direction of the position vector of the separation between the center of force and the reduced mass. So one thing they can conclude is that the torque is always 0, and because the torque is basically the rate of change of angular momentum, the first conserved quantity is the angular momentum. Okay, so angular momentum is conserved. Okay. So one fun thing to see is that the angular momentum of the second system is basically just the reduced mass, whatever it does, maybe it orbits around the center of mass. So basically this is just given by the mass of the reduced mass, the position cross the velocity of the mass. And this thing is going to be constant. All right. One homework exercise that I would like you to do back home is that this basically also says that the angular momentum in the first picture of the two bodies is also conserved. So in this case is m1 r1 cross the velocity plus m2 r2 cross r2 dot. Okay, is also conserved. So I'm not going to do this here, but I hope you do it in your own time, and to convince yourself that everything that is happening on the second picture also translates to the things that happen in the first picture. So if the angular momentum of the second picture is conserved, the angular momentum of the first picture is also conserved in terms of their own coordinate systems. All right. So what is the angular momentum of the second system? So the angular momentum of the second system, we can put the center of mass fixed over here, and the reduced mass fixed over here. All right. So basically, the first thing that you can and we can put the origin at m, and then this is basically x. Sorry, this is basically x, and like x dot, like the the reduced mass can basically go anywhere. One thing that to first look about is that if we look at the angular momentum of the system, okay, we can see that it's the angular momentum points in the direction perpendicular to both the position and the velocity. So in this case, it points outside. It points outside the plane. Okay, the angular momentum points outside the plane. If, for example, if you don't draw it like that, if you, for example, draw in the case that like the angular momentum, the velocity is coming out of the page. The velocity is coming out of the page, then the angular momentum is always in the page. What I'm trying to say here is that wherever your position is and wherever your velocity is, the angular momentum always points perpendicular to them. And in this case, for all two-body systems, that L dot x must always be 0 because they are perpendicular. Okay, this might not be perpendicular, but L dot x must always be perpendicular. So the dynamics of this reduced mass always lie in a plane. Okay, dynamics of reduced mass always lie in a plane. Okay, the dynamics is always planar for a two-body system, so you can always find a plane where okay, like xy, where the entire system of the mass that the reduced mass, okay, just goes about, okay, basically just this, and the angular momentum always will point perpendicular to the dynamics in the plane, okay, and the plane that this the is moving in, okay. This is nice because then we can say that, okay, we can always deal with this in a 2D plane. We don't ever need the 3D description for the reduced mass and for any two-body system. So we can always stick ourselves to the xy plane and put the center of mass at the origin. And the reduced mass, okay, again, let's we'll have position and velocity x and x dot, okay, where then we can finally come to understand what the angular momentum of this particle of the reduced mass is. Basically, we can write this in terms of polar coordinates. All right. So in polar coordinates, we have that that the position of the reduced mass is distance r from the origin. Okay. In the radial direction. Okay, and this is the angular direction, if you remember from Zizong's lecture. And then the velocity can be written as the velocity in the radial direction plus an angular velocity r dot in the perpendicular direction in the plane. All right, or something like omega r. Right. So if you take the cross product between x and x dot, the only possible thing that can come up, all right, is the product of this term, and because r cross r is 0, the only product is this term, and you can write that the angular velocity of the particle is outside of the plane, and its magnitude is basically mu r squared theta dot. And remember, this is a constant of any two-body systems with mutual interaction. Okay, the angular momentum of the particle can always be of the reduced mass can always be written in terms of this, and this is always going to be a constant. So you can always like anything that has combination of r and theta dot can always be written in terms of the angular momentum, which is a constant in the problem. All right. Up to now, has everything been clear? Okay. So good. So we have the first thing. Have the first, conserved quantity that we have. Remember that's the first quantity that we have. The second conserved quantity, okay, is something called the area, which is not actually a separate, not a separate quantity that's conserved, but is a rate of area, I guess. Rate of area. It's not something that it's not something that is, how can I say this? It's not something that is completely tangential or completely, independent of the angular momentum. But basically, what this tells us, it's just saying that, okay, if we redraw a system again, with again the mass, the center of mass fixed at the origin, and the reduced mass here. At some point, the mass, if it has some velocity here, right, or x dot, this mass, this reduced mass will start to trace out a curve. Okay, maybe that's quite bad. Just want to draw it. Let's put it here. So the reduced mass will start to draw out a curve. Okay, that's bad. So draw out the curve, and then at some time t. So at some time t, it was here at t, and then at some next time t plus delta t, it has moved a little bit. Okay, and this the movement of this of the reduced mass would sweep up an area from the center of mass. This is really interesting because if you start to wonder, okay, what's the area? What's the area, swept out by the reduced mass? This is basically, okay, this is equal to this. Okay, first of all, this looks like something of a wedge of a circle, so it has some radius r, okay, which in our case is x. Sorry, yeah, we use x, we use r, so some radius r, and in the same time, like, okay, if this slice is small enough, so if you think about this slice, if it goes small enough, okay, the radius does not change much when the reduced mass just moves a bit. Okay, so if delta t is small, this area is also the radius, the length of this wedge is also r. Okay, if dt is small enough. Okay, the other side of this wedge is also have about the same radius, and then this looks like, okay, this really starts to look like a segment of a circle. Okay, this really looks like a segment of a circle, and we know, okay, what is the area of a segment of a circle? It's basically just a half r squared. Okay, and then this small little area that the circle draws, that the reduced mass draws out, okay, is d theta. Okay, and so this is the small area swept out by the reduced mass in a this is a small area swept out with a reduced mass in a small amount of time that the reduced mass has traveled. And if you stare a little bit closely, remember that we had that our angular momentum had is a constant, which was mu r squared theta dot. If I divide the equation above by the amount of time that the reduced mass has swept has got undergone motion, this is going to be d theta half r squared d theta dt, which in our notation is half r squared theta dot, and this is a constant. Is that okay? So this is a this is a peculiar thing about central forces, or sorry, like two body interactions. Just because the two bodies have a mutual force, they can always be written in terms of be thought of in terms of the a center of mass that's not accelerating and a reduced mass that's just going around, just moving around. And because the force in this system always points towards the center of mass, the angular momentum is always constant, and because of that, the area swept out by this reduced mass is always constant. In the rate of area swept out by the reduced mass is always constant. Has anyone seen something like this before? Like, has anyone seen any other thing that gave you a rate of area that is constant from other like from other places? Like, have anyone seen something of similar? No. Okay. Okay. Maybe not. So just a aside. So this is if you have heard about Kepler. Kepler has laws of governing, motion of planets around the sun. Okay, motion of planets around the sun. In his work, he talks about the planet always draws out equal area in equal time. And basically, this is what Kepler was saying is that the planets draw out equal areas in his orbit when in the same amount of time. But basically, like it's not a law about planets. It's not a law about our solar system. It's just the fact that like between the sun and the planet, there's a two-body interaction, and the force is always towards each other, so they can always be analyzed in terms of the center of mass and the reduced mass. And basically, that just tells you that this is constant. It doesn't matter if it's a sun or a planet that's doing this, or two black holes that are doing this, or even just two blocks of blocks connected by a spring, and you just give them velocity, and then they wobble around. All of them will sweep up equal areas in equal time. Okay, so this is just a matter of fact of that angular momentum is constant, and the two bodies basically just interacting with a mutual force. Okay, so this is the second thing. It's kind of cool. Okay. Were there any questions about this equal area in equal time or rate of area is constant thing that we just talked about? Okay. All right. So if there isn't any question, we could move on. Okay. So yeah. So remember what we were saying? If it's not a circle, will also be conserved. Yeah. So basically, like, okay, the thing we have done here is saying that when we derive this part, okay, this part over here, we basically take the limit when dt is when the mass or the reduced mass only just move a little. So this is a very, very small area, and we're just looking at the amount of the rate of the area that it sweeps out. So of course, like if you do this like completely, if you think about it for if you really take the curve like very largely, maybe like okay, I don't know, okay. Of course, that these two lengths are not really. So if the reduced mass goes from here to here, all right, this is the two lengths are really they're not really similar, okay, and not really equal. So you can't treat them equal. But what we're doing is this is a large time, right? Large time that has traveled that has gone through between the 2 points. What we're trying to do is really push these 2 points really close together. So we're really thinking about the limit when this goes really, really near, really, really near, right? So as long as it's like really, really near in a time step of dt, then the two distances between the reduced mass and the origin should be similar. So this really small area over here can always be written as 1/2 r squared d theta. All right. So we're really talking about the area swept out in a very small amount of time. Okay. Does that answer your question? All right. Cool. Are there any more questions? Okay. If not, let's move on. Okay, so remember what we were talking about? We're trying to look at, like understand the dynamics of the reduced mass. Before understanding completely fully, it's helpful to look at conserved quantities to get a handle of things. So the first thing we had was angular momentum, all right? And the second thing was this rate of change of the area, okay? And these are connected. And the third one, uh, is that, okay, because of the entire system is not acted upon by external forces. All the forces are so are the center of mass is non-necessary thing, so no external force system. Okay, and so when there are no external forces, uh, uh, okay, this is not really true, but for most of the time, we know that there's no energy that's going to be dissipated anywhere else. I'm going to leave this as a homework, actually. So that M1, what you should do is to see that M1 R1 dot squared plus half M2 R2 dot squared plus the potential energy. So where the potential energy is defined as such. Okay. So maybe I should say that for a conservative central force. So if the force is conservative, the neutral force between the two are conservative, then basically that the energy of the system is conserved. And also, then, sorry, this should be an R1 and R2. Sorry, this should be X. Should be X. This should be X. Okay. And also then, you can always translate this into the the system in terms of the reduced mass, where the total mass has a kinetic energy of like this, and the reduced mass sorry, Q of x. Then this is also constant. Okay, try to prove this. Okay, so this is so basically what you want to prove is that dE, the rate of change of the energy is 0. So prove that this is constant by proving that dE dt is 0. Right. So that's going to be a homework, but this is something I'm just going to put it out here, that the total energy is also 0. All right. So these are the three things, okay, that are conserved in the system. Okay, the first thing is angular momentum. So just a recap. The angular momentum basically L equals to mu r squared theta dot okay, in the direction perpendicular to the to the position, and the velocity is always conserved. The second thing that's always conserved is the rate of area change. Okay, so dA dt is equals to half r squared theta dot. This is conserved. And the third one is the total energy. So this I didn't prove, but I just hope you can accept it for now, and you can try to prove it in your own time. So so mrcm dot squared plus half mu x dot squared minus and plus u of x is conserved. Okay. All right. Good. So let's try to understand. Now we have a better understanding about the entire system. We can try to actually understand, solve the dynamics of the system. Okay. So remember that the dynamics of the system is the reduced mass obeys the force law. That looks like this. Okay. But this is very difficult to solve. That's why I talked about energy. Okay, so it's first to look at the energy of the system, or you can. So we want to solve this, but it's very difficult. So let's just look at the energy of the system first, which can be, I think, like Zizan has shown you, that this can be taken as the integral of the equation of motion. Okay, but basically we have seen that basically x dot, right? Sorry. Basically, let's just take a step back and look at the energy of the system. Okay, so one of the dynamics of the system can actually just be seen by looking at like the total energy of the system. So remember that x dot is the reduced mass basically traveling in some direction. So and it has it has the form of the rate of change. So basically this x the velocity of the particle of the reduced mass can be decomposed into the rate of change in terms of the distance from the origin, and also a angular velocity, all right, that makes it go round and round the origin. So there's two components, and so x dot squared is equals to like r dot squared plus r squared theta dot squared. Okay, this is x dot x dot. Okay. And so, but remember that, but because the angular momentum is conserved, is mu r squared theta dot, we can write x dot squared as r dot squared. Plus, remember that because we have this this angular momentum that is conserved, I can always write theta dot in terms of L. So this is L squared divided by plus mu r dot squared plus theta dot squared, which is mu r to the fourth. Okay. Sorry, mu squared r to the fourth. All right. So the energy of the particle is a half mu r dot squared plus sorry, this is r squared here. Oh, okay, let's write this a little bit clearer. So this is r squared and theta dot squared, which is L squared divided by mu squared r to the fourth. Okay, so what we have for the energy is half mu r dot squared plus L squared mu squared r squared. Okay, plus the potential energy. Yeah, so in this case, let's just call this r. And is equals to, half mu r dot squared, which tells you how far away, the kinetic energy of the particle moving away from the origin, plus something that only depends on r. Remember, this was the angular velocity. This is like the angular velocity, the kinetic energy from the angular velocity of the reduced mass, and then plus the the potential energy. Okay, but this is only a function of r, as you can see. So what we can do is to understand the dynamics in terms of some effective potential, where the effective potential is equals to L squared divided by 2 mu r squared plus the potential energy between the two. All right, and we can start to draw this, and basically, if we plot out the effective potential of r respect to r, this will be okay, maybe some random curve over here. Okay, let's just say some random curve, and then the total energy of the system may be some value over here. Okay. And then we can sort of understand what the dynamics are. Okay, so remember this is the total energy, and it must split between the kinetic energy of the particle moving away from the origin, and then some effective potential of the particle that I've drawn here in the purple graph. And this tells you a thing or two about the particle, the motion of the reduced mass, is that given some energy, this particle could be stuck. Okay, like it can only take positions, like minimum positions over here and maximum positions over here. So it's possible that the particle is undergoing some motion that is stuck between two positions, two different positions from the minimum to the maximum. Okay, because like at this point, okay, equals, so at these points, E equals to U, the effective. So what this tells you is that is at this point there's no change in the angular in the radial velocity. So this particle, like when it reaches these points, it must turn back and must turn back and move to places with lower effective potential. Okay. So what this tells you is that there are some energies in which these this reduced mass is bounded by R min and R max. So you have the center of mass over here, okay, and then there's a there's a minimum radius from the center of mass and a maximum radius from the center of mass, in which the particle mu can undergo motion. So sorry. So it can go on and on and on, whatever it wants to do, and then hit one of those and must go away, and then hit one of two and must go away. It sort of does something like this, okay? Sorry, it doesn't. Oops. It must. Oops. Okay. How do I? It must move until it hits one of the boundaries, and then come back together. Right? Come back again. So it must oscillate between the minimum radius, the circle of minimum radius, and the circle of maximum radius, and this allows some bounded motion. Okay, we haven't solved the equation of motion at all, but just by analyzing that the effect that the energies can be separated into something that only depends on the rate of change of the rate of change of the rate of change of the distance from the origin, and something that and an effective potential that only depends on the radius, we can know that the motion of the reduced mass is bounded without solving any of the equation of motion. All right, this is bounded motion. Okay, so this is something that can happen. All right. All right, and remember that the equation of motion is r dot squared plus this if the energy is 1/2 mu r dot squared plus the effective potential. You can see that you can, by writing the r dot specifically as dr dt, okay, you can take dr dt squared to be equal to uh, 2 divided by mu e minus u effective as a function of r. Okay, and get that the time, the period between the reduced mass going from r max to r min must be equal to the integral dr divided by the square root of 2 over mu e minus u effective r. For a cycle, okay, but this is equal to 2 times from r min r max dr 2 mu e minus u effective of r. Okay, so there's a periodicity of the motion that basically between r min and r max just by understanding the energy, and then from that you can already like if you know what u effective is, you can try to calculate the period it takes to go between the minimum radius and the maximum radius. And this is this motion is universal for all two body interactions via mutual force, right? We'll get into more specific details later, but this is just a very general overview of what other motions that can happen if you have two bodies interacting with mutual force. And this is one of them, a period. So maybe I should write this down. So two bodies interacting with mutual force can be periodic separation. Okay, so this is one thing that we have seen. I remember, like, every time we do any analysis between the center of mass and the reduced mass, remember that this can always be translated into, the actual two body motions. That these two, instead of just just orbiting around each other, they can also oscillate, and this also the oscillation between the two bodies, okay, as they go around each other, the periods can be easily found by this integral over here. Okay, not necessarily saying that you need to know how to do the integral, but the periods between between oscillations can be found. Uh, are there any questions up to now about the big picture, that there's some bounded motion that can happen if the and if the effective potential looks like this. Any questions? No. Okay. Okay. Let's move on. So again, we have been trying to understand two body interactions without really solving anything, not solving any equation of motions. But at some point, we really need to understand what's happening. Okay. So uh, we're gonna really try to understand this equation. Mu of x double dot is equals to mu of x f of x in the x direction. Okay, so we're really gonna solve this formula solve the equation right now. One thing I will say is that, okay, I don't know if Susan had taught it in the first lecture or the second lecture, but because I should write this, because the equation of motion is a involves a 3D vector of the separation. So remember that x is equals to r hat, x dot is equals to r dot hat plus r theta dot theta hat. Okay, again, I should draw the picture that if this guy has a position here and a velocity here, this velocity can be decomposed into a radial velocity, okay, and a tangential velocity. But if this guy also have an acceleration, okay, sorry, acceleration is always here. But yeah, in this case, the acceleration is always towards the actually, is that true? Okay, that's not actually true. This guy also should have some acceleration. Sorry, the acceleration should always be in this direction. But okay, because it's a central force, remember. But this is not necessarily equal to only to the rate of change of the particle. Instead of some complicated thing that you should know how to derive from Zizhen's lecture. In this case, we'll just analyze this very very hand wavingly, by knowing that if this is the center of mass and this reduced mass is trying to only has the acceleration between it, it can do two things, right? One thing it can do is to one thing. So maybe this. Sorry. So maybe this thing, if it undergoes some motion over here, okay. Maybe let me use a different color. Okay. If it's traveling this direction, that's not towards the center of mass. One thing it needs to do is it need to supply a centripetal force. So basically, this is something that's like mv squared over r, or mu v squared over r, but is r theta dot squared. And one thing it can do is to just move outwards, accelerate outwards. Okay, so the force in this case, let's make the force outwards. The force needs to do two things. All right, the force needs to let it accelerate outwards. It also needs to counteract. It also needs to supply the centripetal force for it to undergo some motion. Okay, so basically this thing over here, we know that it's going to be r double dot minus r theta dot squared in the r direction, plus something in the theta direction that is 0 because our force here only points towards the center, which is r. Okay. So the equation of motion can be written only can be written just in the radial direction. All right, as just written in the radial direction as mu r double dot, okay, minus mu r squared theta, mu r theta dot squared. This is basically the what's this called? Sorry, I'm blanking out. This is the centripetal force. Okay, let's write it down. The centripetal force must be equal to in this case f of x divided by mu. F of x, f of r. In this case, because we now only care about the radial direction. We decompose in the radial direction. For the sake of discussion, let's say this force is attractive, so it points inwards. So for the matter of case, let's say this is an attractive force. Okay, but we will deal with like repulsive force later. Okay. Is there any questions up until now of decomposing the equation of motion into the radial writing it down in the radial directions? Okay. Is there any questions of this? Good. Okay. If there's no further questions about this, we can now sort of solve this equation of motion. It looks scary, but there's a way to do it. So here's a trick on how to do it. If you ask me why this trick can be done, I really don't know. But it's a trick that you can always use for two-body interactions. Is to define a new variable, which is u equals to 1 of r. Okay, and rewrite everything. Okay, in terms of u. So let's pause for a moment and see what we're trying to do here. We're trying to understand what is the dynamics of the reduced mass, going around the fixed center of mass over here. There's a curve that this is a very bad curve. Okay, this is a worse curve. So maybe let's just draw this nearer so I can. Anyways, there's a curve that this reduced mass draws out as it undergoes some motion. I'm sorry, x dot. All right, and we're trying to understand what the dynamics of it. Okay, the dynamics can be two things. It can either be, how does the position of the reduced mass changes time, Another thing we can try to do is to understand this curve. Like, what is the curve? Okay, what is the curve drawn by mu? Okay, this is the question we're trying to ask in thermodynamics. Is like, okay, what is the path that's traced by mu? This should be reminiscent of the second lecture that when if we just have uniform acceleration, what the curve that's drawn out is always a parabola. Okay, we're trying to ask the same question here in terms of dynamics. If it's not a constant acceleration, what is the curve drawn by two bodies interacting? All right, and the answer is solving the equation of motions. And to do this, we're going to use a trick to do u equals 1 over r. And because we want to understand the curve, we don't want to solve this as a function of time. We want to solve this in function of the coordinates. So in this case, a parabola, it can be written as x squared equals to so a parabola is something like y is equal to ax squared plus bx plus c. So we want to understand in terms of coordinate 1, in terms of coordinate 2. So in this question, we want to understand what is r as a function of theta. Okay, for a curve on the plane, this is a nice way of understanding what the curve look like. We want to understand what's the position of the reduced mass when it's some angle from when it's at some particular angle. Okay, so we want to solve for r of theta. Okay, and if we use this trick u equals to 1 over r, we can do this because we can know that r dot or dr dt, we're going to need to write this in terms of r's and thetas. So hopefully we have something like dr d theta. Okay, but this is not true. We need to multiply by the chain rule. You need something that's d theta to cancel out the d theta here. Okay, so this theta is to cancel out this d theta here. And I also need something that recovers the dt over here. Okay, so I need something to recover dt. Okay. Okay. Again, we use this trick to say that r is equal to 1 over u. Okay. So, sorry. So let's just do d theta dt. Okay. But if we want to express in terms of this this u thing, so we can write dr du, all right, times d theta dt. Again, we want to cancel out the u, so you have something like du dr over here. Okay. So this is because this is a helpful trick. And what this gives, okay, is that dr over du is basically negative 1 over negative 1 over u squared, okay, times d theta dt is theta dot, okay, and the sorry, I'm missing something. Sorry, I did something wrong. This is du dt. Sorry, this is du d theta. Sorry. Okay. Yeah. Okay. Times du d theta. Okay. That's okay. So, but remember that we know what theta dot is because the angular momentum is mu r squared. Sorry. Is mu r squared theta dot. Okay, we can replace theta dot with L over mu r squared. And this basically gives us that r dot is basically du d theta multiplied by negative u squared over 1 L divided by mu r squared. Okay, this is r dot. We can take the second derivative, r double dot, which equals to dr dot dt, and basically this is du. Sorry, we can take out the constants. The constants are negative L divided by mu. And as you've seen here, that remember R is equals to 1 over U, so RU equals to 1. So mu squared and R squared cancel out. Okay, so there's nothing else there. And the time derivative basically only acts on du, d theta. Okay. One helpful thing is that we don't want to take a time derivative of this, but it's helpful to take a theta derivative of du over d theta. All right, and because we had dt here, the chain rule tells us that we can't just have d theta here. We need dt, and to compensate for this d theta, I need d theta over here. This is equals to L theta dot divided by mu d2u over d theta squared. And again, using that theta dot can be related with the angular momentum. This will be equal to negative L squared divided by mu squared R squared d2u d theta squared. Okay, or in terms of u, this is negative L squared divided by mu squared u squared d2u d theta squared. All right. So these are the two things. R double dot is this, and R dot is negative L over mu du d theta. Okay, and just to recap, that the equation of motion is mu R double dot minus R theta dot square equals to negative F of R. So in terms of u, this is equals to negative F1 over u. And then mu R double dot is negative L squared divided by mu squared u squared d2u d theta squared minus R is 1 over u dot square, and is basically, remember that theta dot squared is equal to L divided by mu L squared and mu squared R squared, L squared divided by mu squared u squared. Yeah. Sorry, I think there's something wrong here. I think this is R to the fourth. Yeah. L equals to mu R theta dot squared. No, this is L squared. Sorry. This is correct. Wait. Oh, sorry. Yeah, sorry. This is mu R squared theta dot. Okay. So this is, yeah, that's true. This R4 u to the fourth. Okay. Sorry for the hiccup. Okay. And this is the equation of motion that we had. And if we, do some, if we try to do some, do something with this, let's cancel the mu here. It's all over the place. Okay. And then we can take also out the negative sign. Okay. So if you do it right, you'll be left with an equation of motion in terms of d2u over d theta squared. So this is the first term, and the second term I have, instead of u to the squared, I have u to the fourth, u to the 3. So basically, I take this, and this becomes a 3. And because there's a mu u squared over here, this is instead plus u, and equal to, I gonna put everything else here. F1 over u. Okay. This is the equation of motion that we have. So, okay, which is looks very intimidating and very difficult to solve. But let's deal with something simpler. Okay, suppose f of 1 over u, sorry, f of r is equals to uh some k divided by r squared. F1 over u is equals to k u squared. Then the right hand side will simplify to mu over k mu over l squared. Just k mu over r squared because of this because the u squared cancels out with the u squared here. This is a nicer formula, okay? And so there are two questions here. What force gives something like this? So anyone have an answer for that? Like what type of forces have f of r equals to 1 of r squared that gives you this nicer equation that cancels out the u dependence at the right hand side? Is gravity? Yes. Yeah, thanks, Yahaya. So this is a gravitational force. So for the gravitational force, there's something interesting that happening. They give you this really nice equation of motion that has nothing to do with u on the right hand side, and only a term with with a linear term of u in the left hand side. So does anyone know how to solve this equation? So here is a constant. Okay, k is a constant, mu is the reduced mass, it's also a constant, l squared, as we said before, is a constant because it's conserved, so the right hand side is a constant. Anyone know how to solve this equation? I'll give you a hint. It has something to do with our the lecture last week. Does anyone have any idea? Maybe I need to write it in a little more suggestive way. To constant, maybe let's say f is a constant. Does anyone know? Like, does this remind you of some nice any nice equation of motion from last week? Anyone? No. No. Does anyone remember what is the equation of motion for? Yeah. Okay. Thank you. Thanks, Brandon. Thanks. It's an exponential, but in this case, it's not just an exponential. Is an exponential with a imaginary power, or if you guys remember, the equation of motion for a mass on the spring, mx double dot equals to minus kx, or x double dot plus omega squared x is 0. Okay, this is the and if you have another constant force, what does it do? It just shift the equilibrium position to something over here. Okay. So this is something that is oscillatory. Okay, it's something that has a solution. So that is has a solution that is oscillating, right? So what is the equation of motion? Can anyone? So what is the solution? U of theta. Anyone? Or u of theta is equal to 1 over r of theta. Anyone? Anyone? Okay, never mind. It's gonna be, just all right. It's just gonna be, displaced by k mu over L squared. Okay, let's just call k mu over L squared. Uh, let's just call this 1 over, so let's just call this 1 over P for, uh, for now. There's a reason why I'm gonna, why this, okay? So let's just say that 1 over P is equal to k mu over L squared, okay? Plus, some amplitude that we don't know of cosine of a cosine, okay? Okay. Xq plus f prime cosine. Yeah, exactly. So it looks something like this, okay? So if I solve for r of theta, basically, I can or this must be equal to 1 over p 1 plus pa cosine theta. I'll write in a very suggestive way, or instead r of theta is equal to p divided by 1 plus some constant epsilon of cosine theta, where epsilon equals to p of a, and p is equal to k mu divided by r squared. Okay, so this is the equation, okay, for the motion of the reduced mass. And you can see, so what does this equation look like? So first of all, does it have the oscillatory behavior that I said before? Yes, because it has a period, at least for gravity, as a period of 2 pi. Okay, because cosine theta varies between -1 and 1. Okay, and we have R max equals to P divided by 1 minus E, and R minimum equals to P by 1 plus E. So it really does has the look of a center of mass. Then there's a mu, and there are two circles over here of R min. Sorry, not good circles. R max. And the reduced mass basically does this motion around. Okay, let's just do around this, right? So basically, we have found, okay, at least for gravity, what does the curve that the reduced mass traces out in real time? Okay, it basically gives you something that looks like at least I've told you that it looks something like this. Okay, and so and the shape is basically an ellipse shape for f of r equals to k of r squared. Is an ellipse. So what is an ellipse? An ellipse is something that has a long axis. The long axis is something called the major axis, which has a length 2a. Okay, and then from the symmetry point, there's going to be 2 points called the foci, the focus. Okay, and if you draw, so this is, let's call this, R1. For any point on the ellipse, okay, R1 and R2, for every point, okay, for any point xy, for example, R1, so definition of ellipse is that R1, the length R1 plus R2 must be equal to 2a, the major axis of the ellipse. Okay, there are going to be homework problems here. So basically, the homework problem is going to be telling you that, okay, I'm gonna ask you to derive many properties of ellipse. So basically, but the definition of ellipse is basically R1 plus R2 is equal to 2a. And I'm going to show you that it really gives you an equation that looks like the one I showed you just before. The way to do it, okay, the way to do it is to again consider ellipse. Okay, the two focus. Sorry, I should say a little bit more. So there's this distance over here of an ellipse, which I will call AE, where E is less than 1 and larger than 0. Basically, it's just a portion, like how, like if E equals to 1, then this point is over here. If E equals to 0, this point is over at the origin. So basically, this is just telling you, okay, that this E over here currently is now just saying that, okay, how how far away the focus is from the center. As you can see, as E equals to as E equals 0. So maybe I should say that for E equals 0, the focuses collapse to 1 point. Okay, both the focuses are 0 distance away from the center. But for every 2 R1 plus R2, it must equals to 2a. But because it comes to the same point, these two are always the same length. Basically, it is a circle. So E equals 0 is a circle. Well, basically, this E basically tells you of how far away is ellipse from circle. Okay, it's something called eccentricity. Okay, so it's basically E is a measure of how squash the circle is, such that it gives you an ellipse. Okay, so it's just yeah. Okay, basically it's just but basically for now you can just treat it as some parameter that tells you, okay, how far the focus is from the center. Okay, so if I do that, I really don't want to. I want this. Okay, so I will now show you that the ellipse really is the equation traced by the reduced mass. So basically, I can choose a point here, and then I have R1 and R2. Okay, this is AE. This is AE. Okay, this is A. This is A. Okay, and then let me just call this angle over here phi, or theta. Let's call it theta. Okay, so basically, you can write that the length R1 squared, this length over here, must be equal to the Pythagorean theorem of this, right? It must be equal to the Pythagorean theorem given by this. So it must be equal to x squared plus y squared, where y, where y is basically R2 sine phi. So this length over here is R2 sine theta squared plus the x coordinate here, which is 2ae plus R2 cosine of theta squared. All right, but this is also equal to 2a minus R1. 2a minus R2 squared. Because remember that the definition of the ellipse is R1 plus R2 equals to 2a. Okay, and if you solve this in terms of R2, you get that, so let's just do this, is R2 squared sine squared theta plus 4a squared e squared plus R2 squared cosine squared of theta must be plus the 4ae R2 cosine of theta must be equal to 4a squared plus R2 squared minus 4a R2. Okay, and then r2 squared sine square of theta, r squared cosine square of theta. Remember that sine squared plus cosine squared is equals to 1. So this must be equal to r2 squared. So we have r2 squared. Okay. Plus so this is r2 squared, but there's an r2 squared over here, so it cancels. Everything left has a 4a. Okay, there's a 4a over here, so it cancels. Okay, cancels. Okay, what we're left with is e squared is equals to er2 cosine of theta equals e squared plus er2 cosine of theta equals to a minus r2. So if we do a little bit of manipulation, we can get e squared minus a must be equal to a minus e squared. Am I missing something here? Yeah, so there's an a e squared over here. Sorry. Yeah, that makes a little bit more sense in terms of dimension. So we have r2 plus e r2 cosine of theta equals to a minus a e squared. So r2 must be equal to a 1 minus e squared divided by 1 plus e cosine of theta. And if you remember what we... Oops, the broadcasting has gone. So wait. And if you remember what we had before, we had, the equation, the curve that was drawn by the reduced mass just by, solving the equation of motion. Oops. Okay. There's some issue over here. Okay, hopefully this works. So remember that we got this equation over here by just solving the equation of motions and looking at what the curve is drawn by the reduced mass is r equals to p divided by 1 plus epsilon cosine of theta. Is the same thing here in terms of geometry, where I just derive the equation of an ellipse, that the r2 is equals to a 1 minus e squared divided by 1 plus e cosine of theta. Okay, so that is really the equations that are governed by by something acting on a central force, which is specifically have a 1 over r squared kind of force. Okay, but of course, like this, if you have something that's more general, you will have to really actually solve this equation of motion for that specific force, which is a little bit difficult. But here I just want to show you that there's a nice solution where the right hand side has nothing to depend with has nothing to do with u. And in this case, everything reduces to a simple harmonic motion, which you know how to solve from last week. It's oscillatory, so you have a cosine theta, and then you can solve it and directly matches to a geometry of an ellipse. Okay. I hope that was helpful in terms of understanding, at least at least proving for one of the examples of a two-body interaction, that you really have something that's periodic in R2. Remember, we say periodic because there's an R min and R max, and this thing really draws out something that goes, from R min to R max and R min to R max and R min to R max, something that's periodic, and this is really nice. But in general, it can be really something a little bit more, more chaotic, but it really still oscillates between R min and R max. But this is a really nice example that our understanding from the motion from the energy perspective, this thing must oscillate between Rmin and Rmax. Okay. Uh, so I have 15 minutes left. I want to just give a little brief understanding about this equation over here for two bodies. I already forgotten what it is for. It's kmu over r squared. Okay. Okay. Remember that we derived this. So this is for, first of all, it's for 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 f of r equals to r squared. And the second thing is that we have, this was for an attractive force. Remember, this was for an attractive force. Okay, that's the force. This attractive force sign was enforced upon here. Okay, was here where we take the minus sign. The minus sign in the end was canceled out from everything else, but we had this minus sign over here. Okay, which we cancel out here. Okay, so let's think of the possibility that we don't have an attractive force, but instead let's have a repulsive force. What that does is, give a minus sign here in the equation of motion. Okay, so just a quick check of sanity. Does anyone know what the solution to this equation is? Actually, is that correct? I hope that's correct. That gives. Sorry, let me look at this a little bit more to make sure I have the minus sign in the right place. Yeah. Okay. Yes, I think that's right. Yes. Okay. So, yeah. So basically, the equation of motion, as I just with again, I have P is equals to L squared divided by K mu. I also hope that's right. If I okay, let's just check again that hope is right. P K mu over L squared. Okay, sorry. Yeah. So yeah. So we have instead this is equals to 1 over P minus minus 1 over P plus a cosine of theta. Okay, or r of theta is equals to 1 divided by sorry. Yeah, let's just do this very quickly. This negative 1 over P, 1 minus AP cosine of theta. Okay, so r of theta must be equal to minus 1 over P, sorry, minus P. 1 minus, let's just call this epsilon cosine of theta, or is equals to P cosine theta. Okay, just let me check. I think I did something. It looks like I did something wrong. I hope I didn't do something wrong. Yeah, I think this is correct. Yeah. Okay. Cool. All right. So this is the equation of motion for repulsive force, and yeah, as yeah. So let's think about what the exact r of theta maximum and minimum of these are. First of all, when when cosine goes to, okay, something is weird here. Yeah, okay, yeah. So r of theta, it can go for theta equals 0. For theta equals to so okay, let's think about this. For r equals for theta equals 0, this is equal to epsilon minus 1. That's not very helpful. R equals to 90 degrees. Epsilon goes to 0, so this is minus. Sorry, something looks weird. Ah. Have I did something wrong? Okay. So cosine of 0 is 1. Okay, that's correct. And cosine okay. Yeah, that's correct. Okay, sorry for the hiccup. Yeah. So yeah, this is r of 0. So it has something that's a minimum, all right? But if you look into this, there's gonna be a place where cosine theta is equal to 1 over epsilon. Okay. So at this point, what happens is that r of theta, so let's say happens a theta star, r of theta goes to infinity. Okay. So instead of being bounded between r minimum and an r max, there is a theta star where things start to become weird. That r is equals to that the position of the particle becomes infinitely far away. So what is that happening is I will tell you that this is a this shape is corresponding to a hyperbola. I won't prove it here, but it's something that's a hyperbola, and this is because there's a regime in where the effective potential can look something like this, or at least something like this, and then the energy of the particle does not only intersects the effective potential at one point. So it does have a r min, but there is no r max. And once the particle, hits something, hits r min, it continues to move further and further and further away from r max without bound. Okay, so this is this is not in bounded orbit, but what we call an unbound, 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 an unbound, uh, an unbound path of the particle. So this is a solution given the effective potential. And in the case of gravity, this corresponds to basically just a hyperbola where where a part of the reduced mass, so the center of mass can be here. The reduced mass basically comes near it. Okay, reaches an r min. Okay, maybe I should put the origin here. Here. Okay, reaches an r min, and then after it hits r min, it basically flies off to infinity and never come back again. Okay, yeah. So this is one of the potential, one of the few nice things about it, and this is even even outside of the actually this is not for, sorry, this is This is not for gravity. Okay, because gravity is never sorry. This was a bad idea, but it's not for gravity. So, but you still have this thing. You still okay. I think the sorry, the picture is still correct. That the reduced mass basically approaches this mass and then flies away to infinity. But this is not gravity. Okay, this is not gravity. So remember that. So I think the right way to draw this is that it goes here and then flies off. Okay, it flies off because it's a repulsive force. Remember, there's a repulsive force. Okay, repulsive force of F of R is equal to plus K of R squared. Okay, should be at the other focus. No, so it should look like this. It's drawn very badly, but so I think the right way of drawing this should be this thing sort of tries to approach it, then flies off. This I think this is a more better way of saying it. Anyways, this is a repulsive force, but we still find this repulsive force there in nature. It's not gravity, because gravity is refractive. But basically, you see this in the Coulomb force. And we'll talk more about the Coulomb force next week. But the Coulomb force basically is something that is 1 over R squared and does something like this. And basically, this is scattering. This is a scattering problem. So if you have a positive charge, which is very heavy, for example, so it's very near the center of mass, and then you have a small particle, for example, an electron. What happens is that as the electron approaches the mass, approaches the positive charge, like a proton or an atom, let's just say an atom, nucleus, then the electron basically gets pushed away from the atomic nuclei, and then this trajectory of the electron is basically also defined, given by this hyperbole, because again, this is a two-body problem with a mutual interacting force, which is the Coulomb force, which is basically something like KQ1, K2 R squared. Okay. All right. So for the last few minutes, let's I want to talk a little bit more about scattering, if I may. So I'm just going to give you a brief taste about scattering, and given yeah, Brandon guessed what I'm going to say. Yeah. So basically, this is an experiment that's really famous. It got the Nobel Prize sometime in the past by Rutherford. What Rutherford did is he had some gold foil over here, which consisted of many atomic nuclei, and just basically dump in. Oh, sorry, this was. So maybe it's not electrons. This is bad. This should be something that's a positive charge, whatever. Okay, and the positive charge is an alpha particle, a helium nucleus. Okay, or an alpha particle. Yeah. So sorry, it should be a repulsive force. Okay, sorry for the mix-up. Yeah, and basically from this experiment that Rutherford did by just bombarding the gold foil with helium nuclei, he discovered that bombarding against gold foil, he found that there's some repulsive force, and that basically gives you the atomic nuclei. So what he did was basically seeing so he had just a current which is like of helium nuclei. Okay, so basically this J over here is basically saying how many this is the current of a number current or number flux of helium nuclei. Okay, and then just bombarding towards a gold foil over here. and then just seeing, okay, where did these uh, where did these uh, where did these things land at? Okay, so where did the uh, like, okay, yeah, basically just where things land, scattered to. All right, so this was the experiment that he was doing, and this is really cool. So what happens is that, okay, if we analyze this a little bit, so after time t, if j is constant, then a number of particles uh, has been bombarded and has been scattered off to some random place here to some detectors over here. Detectors. All right. Uh, so after some time t, what happens is that there's some number of particles that pass through is jt, and then there are some number of scattered particles, which should be the number of particles hit. Okay. Uh, and times uh, times some cross section. Uh, times some cross section that it has been that has been scattered, divided by some. So there's a probability that these particles are scattered off uh, and being detected by our detectors. Okay, uh, so by analyzing how the probability of the particles being scattered. Okay, so as a function of of the angle, okay, which is something like d sigma over d theta, we can sort of understand uh, the force that is doing this that is doing this scattering. Because I don't have much time left, so I'm not going to say more about this. I'll include some notes about scattering in the worksheets and handouts. But basically, like understanding like how much of the particles are scattered to the detectors, we can sort of understand the force uh, by knowing knowing how much of these particles are scattered to what angle. Because as you know, like, okay, if you're nearer to the target, you may get deflected more. Okay, so by understanding how much it is scattered as a function of the angle, we can understand the force that is scattering these particles. Okay, but I'm not going to say more because time is up. Before we close the stream, like, do we have any questions? Okay. All right. I'm going to keep the stream up. Gonna end the recording now. But if you have any questions, you can ask. You can